Dear students, in the previous class, we have discussed the method of maximal likelihoods in general. Today, we discuss maximum likelihood estimation of the two-variable model. And remember this, maximum likelihood estimation is extensively used in econometrics because it has many desirable large sample properties. So let us see how we estimate a simple linear regression model using the method of maximum likelihood. Now, suppose that if the two-variable model phi samam beta 1 plus beta 2 xi plus ui, each yi is normally distributed with the expected yi is equal to beta 1 plus beta 2 xi plus ui, and variance of yi is equal to sigma square. Each yi is normally and independently distributed with the mean beta 1 plus beta 2 xi or ui, beta 1 plus beta 2 xi, and variance sigma square. So, the joint PDF of y1, y2, etc. yn can be written as f of y1, y2, etc. yn given beta 1 plus beta 2 xi and sigma square. Each yi is normally and independently distributed with the mean and variance given. So the joint PDF of y1, y2, etc. yn is written as f of y1, y2, etc. yn given the parameters beta 1, beta 2, xi and sigma square. Now given that each yi is normally and independently distributed, this joint PDF can be written as the product of n individual PDFs. That is, f of y1, y2, etc. yn given beta 1 plus beta 2 xi sigma square is equal to f of y1 given beta 1 plus beta 2 xi sigma square into f of y2 given beta 1 plus beta 2 xi given sigma square into f of yn given beta 1 plus beta 2 xi sigma square. Because as we have studied earlier, if x and y are independent, fxy is equal to fx into fy. So f of y1, y2, yn is equal to f of y1 into f of y2 into f of yn, where f of yi is equal to 1 by sigma root 2 pi expected minus half sigma yi minus beta 1 minus beta 2 xi square by sigma square. Each yi is normally distributed. So the PDF of a normally distributed random variable is given as f of yi is equal to 1 by sigma root 2 pi expected minus half sigma of yi minus mu square by sigma square. Now, substituting for each yi, we can write this joint PDF as, so this is equal to, that is, this f of y1, y2, etc. yn given beta 1 plus beta 2 xi into sigma square is equal to 1 by sigma raised to n. Actually, this can be written as a product of three terms. First term 1 by sigma, second term is 1 by root 2 pi, the third term is expected minus half sigma yi minus beta 1 minus beta 2 xi square by sigma square. Now, 1 by sigma into 1 by sigma etc. n times 1 by sigma raised to n. Then root 2 pi n times raised to n raised to n. Then expected. Now consider the third term. It is something like this, e raised to minus of 1 by 2 sigma square. Then this can be written as, say for example, in the form x1, then e raised to minus 1 by 2 sigma square x2, etc. e raised to minus 1 by 2 sigma square xn can be written as minus half into sigma square sigma. So this can be written as equal to e raised to minus 1 by 2 sigma square into sigma xi. So this term is written as, so minus 1 by 2 into yi minus b, not a sigma, because this is only 1 y, not a n y. So sigma minus 1 by 2 sigma square into sigma yi minus beta 1 minus beta 2 xi the whole square minus 1 by 2 sigma square into sigma yi minus beta 1 minus beta 2 xi the whole square using this property. Now, this is the joint PDF of n normally distributed random variables, not simply normally distributed, normally and independently distributed random variables. Actually, this is a multivariate joint PDF. Multivariate joint PDF, and it is assumed that each normally distributed random variable is independently distributed. So it is a special case. The general case will be considered later when we study the same thing using matrix algebra. Now, if y1, y2, etc. yn known, beta 1, beta 2 and sigma square unknown. If y1, y2, etc. yn known, beta 1, beta 2, etc. beta 1, beta 2 and sigma square unknown, this function is known as the likelihood function. Then this joint PDF is written as likelihood function of beta 1, beta 2 and sigma square is equal to 1 by sigma raised to n root 2 pi raised to n expected minus 1 by 2 sigma yi minus beta 1 minus beta 2 xi the whole square by sigma square. So it is a likelihood function. Remember the difference between joint PDF and a likelihood function. This is a joint PDF. If the parameters are known, yi is not observed. On the other hand, if y1, y2, etc. yn known, then the parameters are unknown, then it is a likelihood function. We write it as likelihood function of beta 1, beta 2 and sigma square. Now, the method of maximum likelihoods consists of estimating beta 1, beta 2 and sigma square by maximizing the likelihood function. The method of maximum likelihoods consists of estimating the unknown parameters beta 1, beta 2 and sigma square by maximizing the likelihood function or by maximizing the probability of obtaining the given y values as high as possible or simply by maximizing the likelihood function. So the method of ML consists of estimating the unknown parameters beta 1, beta 2 and sigma square in such a way as to maximize the likelihood function. And remember this, the value of this likelihood function is a function of beta 1, beta 2 and sigma square. So we estimate these parameters by maximizing the value of the likelihood function or by maximizing the value of the joint PDF of y1, y2, etc. yn, that is the observed y values. Now, as differentiating this function is somewhat complicated, or differentiating the log of this likelihood function is more easy, we rewrite this into log terms. And writing the likelihood function in log form will not alter the results. The reason is log likelihood function, log function is monotonic, so that the likelihood function and log likelihood function attain maximum values at the same point. So we write ln LF. ln LF is equal to, the first quantity can be written as sigma raised to minus n. So, and its log is minus n into sigma square minus this root 2 pi raised to n is root 2 pi raised to n is equal to 2 pi raised to 1 by 2 all raised to n. So 2 pi raised to n by 2 and it is equal to 2 pi raised to 1 by root 2 pi raised to n is equal to 2 pi raised to n by 2 or minus n by 2 ln minus n into ln sigma square minus n by 2 ln 2 pi, then ln of e raised to this quantity is the same as minus 1 by 2 sigma yi minus beta 1 minus beta 2 xi square by sigma square. By sigma square. And this can also be written as equal to minus, this is equal to sigma minus n ln sigma minus n by 2 ln sigma square minus n by 2 ln 2 pi minus 1 by 2 sigma yi minus beta 1 minus beta 2 xi square by sigma square. Because we have to differentiate this with respect to sigma square. So this term is rewritten in terms of sigma square, that is all. So minus n by 2 ln sigma square minus n by 2 ln 2 pi minus 1 by 2 sigma. So this is the log of the likelihood function. Now, to find the values of the parameters which maximizes the value of the joint PDF, that is maximizes the joint probability of observed yi values as high as possible, we differentiate ln LF with respect to beta 1, beta 2 and sigma square equated to 0. So first dou ln LF with respect to beta 1 equal to no terms of beta 1 in the first two. So there is a term here. So minus 1 by 2 sigma square into 2 sigma yi minus beta 1 minus beta 2 xi into minus 1. That is minus 1 by 2, sorry, 2 and 2 cancels, minus 1 by sigma square into sigma yi minus beta 1 minus beta 2 xi into minus 1 and minus 1 by sigma square into sigma yi minus beta 1 minus beta 2 xi into minus 1. Then dou ln LF with respect to dou beta 2 is equal to, skipping the first step, this can be written as minus 1 by sigma square into sigma yi minus beta 1 minus beta 2 xi into minus xi, skipping the first step. Then dou ln LF by dou sigma square is equal to, there is a term sigma square here, minus n by 2 into 1 by sigma square. Dou ln sigma square with respect to sigma square minus n by 2 constant into 1 by sigma square plus 1 by 2 into sigma raised to 4. This quantity is minus so this quantity is by 1 by sigma square. It will become sigma square raised to minus 1, and doing the calculations and noting that there is a minus here, become 1 by 2 sigma raised to 4 sigma yi minus beta 1 minus beta 2 xi. These are the partial derivatives. These are the partial derivatives. Now, equating these partial derivatives to 0 and letting beta tilde 1, beta tilde 2 and sigma tilde square as and as the estimators, we will obtain 1 by sigma tilde square into sigma yi minus beta tilde 1 minus beta tilde to xi equal to 0. Multiplying throughout with a minus. This becomes 1 by sigma square into, and equating it to 0 means we are assigning specific values to the unknowns. Sigma tilde square, beta 1 tilde, beta 2 tilde. And second, 1 by sigma tilde square into sigma yi minus beta 1 minus beta 2 xi into xi equal to 0. Assuming that the terms multiplied with a minus here and a minus here. And minus n by 2 into 1 by sigma square plus sigma tilde square plus 1 by 2 sigma tilde raised to 4 into sigma yi minus beta tilde 1 minus beta tilde 2 xi equal to 0. So what I did here is equating these to 0 is equivalent to giving specific values to the unknowns. Specific values to the unknowns. Now, as you can see, from the first equation, you will get, as this quantity is not equal to 0, sigma yi minus beta tilde 1 minus beta tilde 2 xi equal to 0. And from the second, sigma yi minus beta tilde 1 minus beta tilde 2 xi into xi equal to 0. Now solving the first equation, you have sigma yi is equal to n into beta tilde 1 plus beta tilde 2 xi. Second, sigma yi xi is equal to beta tilde 1 sigma xi plus beta tilde 2 sigma xi square. So these are the same normal equations we have obtained in the case of OLS. So it follows that the OLS estimator of beta 1 and beta 2 are same as ML estimator of beta 1 and beta 2, because beta tilde 1 is equal to beta 1 hat, beta tilde 2 is equal to beta 2. So OLS and ML estimators are same. Now let us consider the third equation. Now this can be written, taking these terms to the left, n by 2 into sigma tilde square is equal to 1 by 2 sigma tilde raised to 4 into sigma yi minus beta tilde 1 minus beta tilde 2 xi. Cross multiplying, you will get 2 into sigma tilde raised to 4 by 2 into sigma tilde square is equal to 1 by n into sigma yi minus beta tilde 1 minus beta tilde 2 xi. And 2 and 2 will be cancelled. This becomes sigma tilde square is equal to 1 by n into, this quantity is, I write it as sigma u hat I by n. Sigma u hat I by n. So the estimator of sigma square, that is sigma tilde square, that is the ML estimator of sigma square is sigma u hat I square by n. We know that for the two variable model, sigma u hat I square is equal to, two variable model, sigma hat square was sigma u hat I square by n minus 2. And we have shown that the expected value of sigma u hat I square is equal to n minus 2 into sigma square. So that this becomes n into n minus 2 into sigma square by, and dividing with n minus 2, this becomes is equal to sigma square dividing with the n minus 2. So naturally, if you divide it with the n, it becomes sigma square minus 2 by n into sigma square. So this term is the bias term. So if you estimate sigma square as sigma u hat I square by n, that is the ML estimator is a biased estimator of sigma square. The bias is given by 2 by n into sigma square. And this bias will disappear as sample size increases indefinitely. If the bias disappears as the sample size increases indefinitely, such an estimator is known as consistent estimator. So in the small samples, ML estimator of sigma square is biased, but in large samples, it is a consistent estimator of sigma square. So if you compare ML with the OLS, remember this, both the estimators of beta 1 and beta 2 are same. The difference is the estimator of sigma square. OLS estimator is unbiased, ML estimator is biased. But remember also this point, OLS estimators are based on very stringent assumptions. 7 assumptions we have discussed in the context of simple linear regression model. If these assumptions are violated, then the properties of OLS estimators will be adversely affected. And OLS estimators are not very robust to deviations from assumptions. But ML estimators are more robust to the deviations from assumptions. That is why MLS estimators are extensively used. Also, in some cases, OLS will not work. As we will see, when we estimate a logic model, we use ML estimator rather than OLS estimator. So this is the ML estimator of the 2 variable model. This is true for the 3 variable model also, and also for the general K variable model. So ML estimator and OLS estimator are the same for 2 variable, 3 variable and general K variable model. The difference is in the case of the estimator of sigma square. In the case of the estimator of sigma square, ML estimator is always sigma u hat I. There is a square here, sorry. Sigma u hat I square by n. Sigma u hat I square by n, not sigma u hat I. Sigma u hat I square by n. So ML is always biased in small samples, but the bias will disappear in large samples.